We have to be very careful about the language that we use when we're talking about uncertainty. One reason it's so difficult to do this is that we misuse this language on a daily basis in our everyday lives. For example, if I were to say, want to estimate the average height of all adults living in the United States, I might be inclined to say something like, oh, it's probably around 5'9". That probably is language of random chance when what I'm really expressing is uncertainty. There's no random phenomena going on at all in the average age calculation of all adults living in the US. It's simply something that I'm not very certain of. So it might be too ambitious a goal to correct all of the language that we use in every circumstance, but we want to at least know what is correct and what is not correct when we are focusing on it and when we are doing something like interpreting a confidence interval. So, random chance versus uncertainty, when we're talking about sample statistics, we use language of random chance because a sample statistic is something calculated from a random sample. So sample statistics like X bar if we're talking about a mean, P hat if we're talking about a proportion, R if we're talking about a correlation, etc. Population parameters, on the other hand, represent an entire population. There is no randomness in a discussion of a population parameter, for the most part. Here we have uncertainty. The average height of all adults living in the US would be a mean, which we would refer to as mu. It's an average for a whole population. I'm not certain what mu is, but it doesn't make sense to talk about mu using this random chance or probabilistic kind of language. If I'm talking about a proportion, I would use p. If talking about a correlation, that would be that Greek letter rho that looks kind of like a p but isn't, right? And the simplest way that we can see why this difference holds is that a sample statistic comes from a random sample. It is calculated from a random sample of the population, so there is some randomness and some luck or probability involved. A population parameter is from the whole population. It measures some quantity for a whole population. We often don't know the exact quantity because of the fact that populations tend to be large, and in many cases we can't contact the whole population, and that's why we get this uncertainty. So when choosing our language, we want to think about whether we're describing a population parameter or a sample statistic. Looking at this first example here, give this a try first of all. Go ahead and pause the video, read through the description, and then take your best guess at what the correct language is to use to talk about these things, and I will choose it in just a moment. All right, so we are talking about mean age from a sample of 100 breast cancer patients is 53 years, so that mean age is X bar. A 95% confidence interval has margin of error 3 years. So that means that when we go out to the whole population of all breast cancer patients, we're looking at that same X bar, give or take 3 years. So mu is 53, give or take 3. The margin of error always comes in when we go from the sample to the population. So looking at this first statement here, we see that we're talking about the mean age of all breast cancer patients. So that is the population, and therefore the mean age of all breast cancer patients is a population mean mu. That means we are talking about confidence instead of chance. And so I would read this more naturally as there is 95% confidence, not there is a 95% confidence. Anytime we're talking about random chance, we tend to use the word chance or probability. or likelihood. However, when we're talking about uncertainty, we can use the word confidence or confident. That's how we can express uncertainty, is what level of confidence we have that something is true. So in this second statement, we can see that we're talking about the mean age of any random sample of size 100. So that's same sample size that was in our description. That is talking about an X bar, and we believe that that's going to be within 3 years of whatever that true mean age is, which is unknown, right? We're comparing it to an unknown parameter mu, but our statement is about X bar. So here we would say we are talking about random chance because this describes a random sample or a sample statistic, and I would say there is a 95% chance that this mean age X bar is within 3 years of the true mean. And as we go on to interpret the confidence interval, let's take this idea here. We said that the parameter mu is 53 give or take 3. So that tells us that mu is between 50 and 56. When we go to interpret the confidence interval, we want to say something that is equivalent to this, where we, of course, interpret mu in context. So looking at these interpretations, we want to choose the one that really focuses on the parameter mu. The first one says, with 95% confidence, ages of all breast cancer patients fall between 50 and 56 years. Ages of all breast cancer patients. It's good that it refers to the population, which is all breast cancer patients, but we can see that it's missing that parameter, which is the mean. Nowhere in here does it say mean or average, and when we read this again, we realize that this is saying that everybody's in this interval, not that the average of everybody is in this interval. So this is not correct. Looking at the second one, we see that this states with 95% confidence, the ages of 95% of all breast cancer patients fall between 50 and 56 years. This is similar to the previous statement in that it also lacks the word mean or average. This is not a statement about a mean. This is again a statement about individuals. The only difference is that we're now saying instead of all breast cancer patients, 95% of them, still not a statement about the mean. This is definitely not true. The very last one, with 95% confidence, the mean age, so that's our parameter, that's mean, for all breast cancer patients. We see that this is a statement about the population mean, not about a sample mean. So putting these together, we can see that this is a statement about mu is between 50 and 56 years. This is the only one that really states that mu is between 50 and 56, so this one is correct. Now, the explanation of 95% confidence, this is going back to the idea of what does that confidence level mean interpreted as a success rate. Remembering our example with the comic, we said we would find that confidence level by calculating the success rate over many different estimates. So if we followed the same methodology each time and estimated the high temperature, or the high temperature in a range, within a range, then whatever percent of the time that methodology would give us a correct answer is the same thing as the confidence level. So we want to take that idea into what we're reading here. The first statement, the mean age of all breast cancer patients, so at least this is a statement about mu, so that's good. That's mu. Is between 50 and 56 years, 95% of the time. Well, mu isn't changing, right? And we're not really considering whether mu might change over time because that's not part of the definition of this particular mu. Mu is a fixed value, so it's not possible for it to be between these years sometimes and not between these years other times. So because mu is a fixed value that we are trying to estimate, it's not really possible for us to talk about it this way. Now this next one says there is a 95% chance that the mean age of all breast cancer patients, so we see that again this is about mu, is between 50 and 56 years. Well, again, we're going back to that language of when we can use probabilistic language and when we cannot. We are never allowed to use that probabilistic language of random chance, when we're talking about a population parameter, such as mu. So this statement is also incorrect. Now let's jump down to the last description. There is a 95% chance right off the bat. We know that that's a little scary, but look, it does describe X bar, right? It does actually describe a sample statistic. So at least using the language of random chance with a sample statistic is correct. However, we know that the real meaning of the confidence interval is that it's where we believe that mu is. So the connection of probabilistic language with a sample statistic is fine. That part of it's good. However, the confidence interval itself describes mu. It does not describe lots of different random samples from the population. So this should describe mu. Only mu is believed to be in this interval. It is not true that 95% of the random samples that we would generate would necessarily be in this interval. Mu might be very close to the edge of this interval, and that's really why it's problematic to go back to thinking about it this way. We think that mu is between 50 and 56. Mu might be 50.1, and there I am again saying might be. Sounds a little bit probabilistic, so that's an example of how we misuse this language. But it's plausible that mu is 50.1, in which case it would certainly not be true that 95% of the random samples from the population would be between these two numbers. They would be between two numbers that are centered closer to that 50.1. And that's why we can't reverse this kind of description and apply it to X bar. So the only one remaining, of course, we believe needs to be right, but let's go ahead and see why it's correct. The mean age of all breast cancer patients, that's definitely mu, is believed to be between 50 and 56 years, so there's no probabilistic language or random chance language in that. The success rate of this methodology is 95%. That is in keeping with what we said about the weather predictions, right? If we were to do this process over and over and over again, where in this case the process is I'm going to go out into the population and generate a new independent random sample, and from that independent random sample calculate a confidence interval, right? If I were to do that process over and over and over again, then I would expect 95% of the intervals resulting from that process to contain the true value of mu. So this is our correct answer. I didn't mean to use red there. So another thing I want to call attention to while we have these examples up here is the difference between these two instructions. We have interpret a confidence interval. This is asking for the correct interpretation of a confidence interval, but that's just a slight difference in the wording based on the fact that it's multiple choice instead of asking you to write it yourself. The explanation of the meaning of confidence is a totally different instruction. So it's easy to mix these two instructions up. When we're asked to interpret a confidence interval, all we are being asked to do is explain what that confidence interval tells us about the population parameter in context. It's not getting into any details about what 95% confidence really means. We summarize all of that with this simple statement with 95% confidence, and we leave out that explanation. If we're asked to explain the meaning of 95% confidence, or it could be 90% confidence or 99% confidence, that's when we get into this idea of it being a success rate, the success rate of a methodology. It's estimating a population parameter, right? And it's really assuming that the same methodology is used in all cases and saying how many of them would contain the true parameter mu in this case, or p, or whatever our parameter might be. So it's important to know the difference between these two instructions so that you don't answer the wrong one, say example on a test when you're asked to do one of these two things.